In this video, we're going to explore hydroboration and oxidation of alkenes. In the first step, we take this molecule borane and add it in a Markovnikov fashion. A reminder, the electronegativity of boron is 2.0, which is lower than the electronegativity of hydrogen, which is 2.1. More electronegative atom on the more substituted carbon is Markovnikov. Less electronegative boron on the less substituted carbon, the other half of the Markovnikov definition. This happens 3 times, and each time is progressively faster than the previous, because as you replace bonds on boron to hydrogen with bonds on boron to carbon, the boron becomes more positive, which makes it more attractive towards pi electrons. Reaction's called hydroboration because it adds a hydrogen on one side and a boron on the other. We're going to discuss why it's called Syn Stereoselectivity. That's SYN. Because in this reaction, both of these bonds happen at the same time, so they must happen on the same face of the double bond. Syn meaning they happen on the same side. That's a very short mechanism we will see shortly. The oxidation step is our biggest step of the semester, and it replaces the bond between carbon and boron to a bond between carbon and oxygen, creating an antiMarkovnikov alcohol. And this reaction also happens 3 times, generating 3 alcohols from one trialkyl borane depicted here. These 2 R groups here are identical to this R group here. There's the name of the R group. I apologize, the name of the R group is up here. The name of this molecule has the name of the R group in it. There's 3 of them, 2 ethyl cyclohexyl groups attached to boron. Boron alkanes are called boranes. This would be the equivalent of methane, the boron version. Over here we have a review of earlier videos that put water onto a molecule. Yes, I know it looks like we're only putting hydroxide on these molecules, but I want to point out in this product here, there's a CH3 on the end, and there was only a CH2 on the end to start with, so the extra H from water goes there on the end. In this product, the H also went on the end, CH3 versus CH2. And in this product, the OH went on the less substituted carbon, and there's a new H here, CH2, whereas before it was just C with one H. So every product involves adding water. Also down here, every product involves water. There's only one product in this case. And this is the previous video we did on oxymercuration demercuration. And the main advantage of it's actually illustrated here. We do not get any rearrangements with the oxymercuration protocol. You go straight. And I notice there's a mistake in this product here, which I will fix right now. In the oxymercuration step, the more electronegative O ends up in the more substituted carbon, right here, and the less electronegative mercury on the less substituted carbon, right here. In the demercuration step, which wasn't really covered in the video, mentioned in the comments and mentioned here, demercuration replaces the mercury with a hydrogen, which I noticed the other mistake here. The hydrogen replaces the mercury with sodium borohydride reacting with this carbon-mercury bond. Side products being metallic mercury, which is a liquid, very dense, it would be at the bottom of the flask, and acetate ion, which comes off of the mercury. Side products we don't worry about too much in this class. The important thing is you made a high yield of the Markovnikov alcohol here, and you got a very low yield of the same alcohol doing it here because rearrangement to a tertiary carbocation gave a better cation here. No carbocations in 6.1G. No rearrangements. Very important. The whole motivation for this new video is down here. How can I get a very high yield of the antiMarkovnikov alcohol, whereas before it was only a very small amount of this reaction and you got none of it in this reaction. Alcohols are a useful functional group in organic chemistry. We must be able to make any kind of alcohol anytime. We're going to start the mechanism with the hydroboration step. The boron, being less electronegative than hydrogens, has a slightly positive charge. That makes the boron more attractive towards the electrons than the hydrogens. We have not seen this until now. Mechanism starts with the pi electrons of alkene being attracted to the more positive atom boron. Now, if this was the only arrow in this step, we would generate a carbocation. You guessed it, right here would be the major, generating a tertiary carbocation, as opposed to up here generating a secondary carbocation. Making a fourth bond to boron, which is what this arrow would accomplish, would create a negative formal charge on boron. It's in the third group on the periodic table. Hydrogen being bonded to a boron that has a formal charge of -1 basically says, I'm taking my electrons and making a more stable bond to carbon right now, and there's a reason why it goes to the more substituted carbon, and I hope I start sounding like a broken record. The reason why the hydrogen comes back to the more substituted carbon and not the less substituted carbon is that this carbon spends more time with a positive charge. Why does this carbon down here spend more time with a positive charge after this first arrow than this carbon? Simple answer, hyperconjugation makes tertiary carbocations more stable than secondary. A recurring theme in all of Chapter 6. The result of this reaction would be this product here. Here's the result. As promised before, the boron is now even more positive than it was before because it's now bonded to a carbon, which is more electronegative than the original hydrogen. That means this boron is attracted to yet another one of these alkenes, and it will be attacked by another alkene, making a new molecule here where an H is replaced by another carbon group, and then it will happen a third time up here, and the end result will be this up here. You would repeat the process 2 more times. Once again, I am not into making you do the same mechanism over and over again, so you will only show me 1 time. I will show you how it looks on tests very shortly. The only question we haven't addressed is why are the boron and hydrogen on the same side of the ring? And the reason is we have a new selectivity. The name of the stereoselectivity is Syn, and we see stereoselectivity occur, both new bonds occur at the same time. Please recall we observed anti-stereoselectivity when we had a triangular intermediate which then underwent a backside attack to create an anti-stereoselectivity. We do not have a triangular intermediate here. This arrow here creates the bond to boron. At the same time, this arrow here creates the bond from carbon to hydrogen. Here I showed wedge-wedge. you'll get a 50-50 mix of wedge-wedge and dash-dash. Let's look at how I would test this on an exam. So on an exam, I would already have two of the R groups on the boron. Here is one of the R groups drawn out. Here's the other R group stated by this statement here. And here's my third alkene. You'll only show me it reacting one time. Pi electrons attracted to the less electronegative boron, and the hydrogen takes its electrons and goes to the more substituted carbon. I'll clean this up in a second. Pi electrons attack the boron. Sigma bond goes from B to H, makes a bond from H to C, giving this result here. This is the test version. I see that this video is starting to run a little long, so I'm going to break it up into two parts. So far we've covered hydroboration of an alkene to yield what is currently a Markovnikov result. A gentle reminder, boron's electronegativity 2.0, hydrogen 2.1, less electronegative boron on the less substituted carbon, more electronegative H on the more substituted carbon. Markovnikov. This ends part 1 of this exploration.